The light of our lives comes from the sun and other stars. A form of electric and magnetic energy, photons of light travel through space, behaving both like particles and waves. Like ripples in a quiet pool of water, changing electric and magnetic fields of light can be seen far away from their point of origin. Light travels at a constant speed for hundreds, thousands, even millions of years to get here. There's distant light in the universe, billions of years old. Even the light from the star nearest our sun, Proxima Centauri, takes 4.3 years to arrive, and that's traveling at 186,000 miles per second, the fastest speed in the universe. To collect light, our eyes function something like cameras, with lenses and pupils controlling the amount of light absorbed. Much of the light in space is too distant for our eyes to see detail and color without assistance. To peer farther into space, Galileo pioneered the use of a telescope in 1609. Like all lenses, these refractor telescopes bent parallel rays of light passing through glass and converged them on a single focal point. Images were magnified with an eyepiece. These early telescopes collected no more light than modern binoculars. To see farther, these telescopes would need to become larger, but they could only grow so much. Lenses wider than 3 feet may distort, causing a distortion in the image as well. Refracting telescopes gave way to reflectors. They bounce light from one or more reflective surfaces to a prime focus. Reflective mirrors need less support than lenses and can be made larger than refracting telescopes. The mirror on this reflector is nearly 14 feet across. The reflector has 2 mirrors. Light bounces off the big mirror, then off a small mirror to a focal point where it's recorded and stored electronically. Today, the largest reflector telescopes are in Hawaii, on a 14,000-foot peak called Mauna Kea. The Keck telescope's 2 mirrors are more than 30 feet across and are made in movable pieces that can shift to compensate for changes in the atmosphere. As better and better telescopes help us capture light farther and farther away, we can see light older than man and as old as the universe. Over the last century, we've gone from the horse and buggy to a world teeming with hundreds of millions of automobiles. From the Model T to the latest race cars, one thing remains the same: the internal combustion engine. In these engines, a fine mist of gasoline is sprayed into the piston chamber. When a spark is added, the mixture of air and fuel explodes, driving the piston down and spinning the crankshaft. As the piston moves back up, it pushes the remnants of the explosion out of the piston, and the cycle repeats. Take the unburned fuel and carbon monoxide in that exhaust, multiply it by the number of cars on the roads, and you can see why the automobile is considered such a serious threat to the environment. What if we could power our cars with a different sort of reaction? One that runs cheaper and cleaner than any engine yet. Scientists are getting closer to just such a solution. This bus can run at highway speeds over 100 miles at a time. But unlike diesel-powered buses, it runs with no noise and produces only water as its exhaust. It's powered by something called a fuel cell. A fuel cell produces electricity, but it isn't a battery. Instead, hydrogen and air are run on either side of a membrane. The membrane induces the hydrogen and oxygen atoms to combine in a way that produces water and energy. The cell has no moving parts, runs slightly warm to the touch, and as long as hydrogen and air are provided, can't run down like a battery. The idea has been around for a long time, but until recently was too inefficient to be practical. Then one day an engineer at Ballard Systems looked at a new kind of membrane that had been sitting on his workbench for months. When he tested it, he found that the cells produced 4 times as much power. So far, fuel cell technology is still in the testing stage. And with so much invested in the old gasoline-burning technology, it may be a while yet before we drive fuel cell cars. But with the constant threats of rising oil prices and pollution, there's never been a better time for a replacement.
The polar ice sheets of the Arctic and Antarctica cover 1/7 of the Earth's surface. Because they cap the ends of the Earth, the poles each experience 6 months of near constant daylight and 6 of the darkest winters on the globe. Home of the South Pole, Antarctica is a continent of extremes. The highest, driest, and windiest place on Earth, Antarctica is technically a desert, trapping 70% of the world's fresh water in 90% of the world's ice. There isn't even enough water in the dry air to make snowflakes here. Instead, Antarctica produces diamond dust, best seen at night. A polar meteorologist catches a little dust and unveils its flat, hexagonal shape under a microscope. During the day, diamond dust creates an eerie halo in the sun. Over millions of years, the dust has collected to create an ice cap 3 miles thick. But at the opposite end of the globe, the North Pole boasts the largest expanse of sea ice. An ocean of ice covers 5.5 million square miles. Shipping lanes choked with ice make dangerous highways, and ships with bows made of 12-inch steel must crack and cut their way through. Miscalculations spell disaster. Ships running the lanes early or late in the 6-month season are often supported by helicopters, charting the safest routes from the skies. South of the North Pole, Greenland glaciers push to the sea and carve as many as 15,000 icebergs in a year. The rogue chunks of ice may tower as high as office buildings, but even greater expanses float unseen below the water's surface. To protect ships from running into icebergs, the U.S. Coast Guard flies an ice patrol. They relay warnings to ships on a collision course.
Go ahead. Roger, got an unidentified target 6 miles off 3 o'clock on the aircraft. Can't see it through the under.
While polar ice poses problems for man and machine, the loss of it may prove more devastating. For the last 30 years, the ice shelves around Antarctica have been shrinking. They're disappearing at a rate of more than 1% every 10 years. Global warming, caused by a buildup of man-made greenhouse gases, makes a little more ice melt each year. Melt all the ice sheets, and the sea level would rise a devastating 200 feet. Remote as they are, the ice cap's influence travels the globe.